Hello and welcome. This is Chapter 2, Section 2. The name of the section is Instantaneous Velocity. It is a topic that we kind of use to motivate review of derivatives as well. So in thinking about velocity, we defined average velocity in Chapter 1. Average velocity was the displacement divided by a time interval. Again, you have to remember what displacement is. Displacement is a difference in position vectors that's found via vector subtraction, and then that is a ratio over the time interval. That's really all you can ever measure. You only measure the average velocity, and you can get a better approximation of the value of velocity at an instant in time by just taking successive approximations of average velocity as the time interval becomes slower and slower, right? As the time interval becomes slower and slower, the changes in the speed should be slower and slower, unless it has some weird bounce to it, right? If you're trying to find the velocity of an object as it's in the instant of time and when it's bouncing off of a wall, then you're not going to get a helpful answer. And the velocity won't really be defined at that point because the final value, the limit just doesn't exist. And so we define instantaneous velocity as a limit, right? As a limit as delta t goes to 0 of the average velocity. And once again, they use the generic s-axis, but it's a limit as delta t goes to 0, not necessarily as delta s goes to 0. Why is it delta t and not delta s? Well, because these, in a more general sense, all these vectors are really functions of time. And the time is the dependent variable. So in the next picture, we have a good pictorial representation of it. Let's say we have a launching rocket and we graph its vertical position as a function of time. We've got s-axis, and this is a curve describing the position versus time. So at initial time 0, or initial time t equals 0, the graph is 0. But the further in time you get, the speed actually increases. And if we zoom in on that spot right there, we'll see that if you zoom in enough, you can't tell the difference between that graph and a line at that specific spot. That means that that's what it means for a function, or that means what it means for a function to be differentiable, actually. So the slope of that line is the incremental change in s divided by the incremental change in t. And once again, you set a limit for that. You might remember from calculus, there's a specific definition of a derivative as the limit as h goes to 0 of f of x plus h minus f of x divided by h. And this is essentially what we do here, just different names. And so we got a slope of the tangent line at that point. That's what that is, right? And that tangent is only that line is only a valid approximation of the velocity within that small region of time. As you can see, the further out you go, the difference between our approximation on the line and the actual value on the curve, the error increases as you get further away from that point. As increment t gets smaller, the velocity v averages approaches a constant or equal value, and that's exactly what we do. It's fun to do some experiments like this where you, one old physics experiment that we used to do was we would have 2 time sensors, 2 photo gates to measure 2 instances in time, or the difference between those 2 times, and we'd have a cart go through them, and those photo gates would be brought closer and closer together, and the closer they were together, the more the calculation of average velocity started to mimic the instantaneous velocity. And sure enough, if you graph that, you can eventually assign a value of instantaneous velocity. But when we're talking about, say, speedometers, radar guns, all these things, these are always only measurements of average velocity. We cannot measure instantaneous velocity directly. All we can say is that this is what the value approaches. You can make the average velocity as small as you like to where you can't even tell the difference with instantaneous velocity. And that is something that's unique to science and physics, different from math, because there is significant figures, right? You can approximate, if you think about the square root of 2, you can approximate square root of 2 with the decimal as closely as you want, but you'll never, there's always going to be a difference. Well, if you're only measuring out to 3 significant figures, you can devise an experiment that measures the average velocity close enough to where the value that you project doesn't differ from what you measured. That's a little trick of physics where you kind of make an experimental value almost a theoretical value, because it depends on the significant figures. So here's another example. You can certainly go through these on your own time when you're reading the textbook. This looks like it says to consider different instances in time of an object that looks like it starts moving down. It starts below that origin, moving downward, but slowing to a halt, and then moving upward, crossing the origin, and then slowing to a halt when you're far away above the origin. And so what are some things that they want you to do here? What would be the points of the maximum velocities? You know, these are just, you have to remind yourself what these slopes and maxima mean in these derivative problems. All right, so point A and point C would both have a velocity of 0. And just because point B is close to the origin doesn't mean the velocity itself is 0. It just means it crosses the origin at a speed equal to the slope. That's exactly what we have. That's exactly what we have on this graph on the lower right-hand side. It's a reasonable graph. I mean, you weren't given a function, an analytical function that describes this curve, this y versus t curve. So the best you can do is make some sort of reasonable assumptions about maybe it's closely linear. But what do we see here is that at point A, that corresponds with a 0 on the velocity graph. At point C, that corresponds to another 0 on the velocity graph. And point B, evidently, is the time where the velocity is largest to the right. So you can almost take an imaginary line at the, that goes straight down from point A on the y versus t down to point A on the v sub y versus t, and you'll see that slope derivative relationship. And of course, we have the assess step, but does your answer seem reasonable? This is just a helpful review of slopes and maxima and zeros. And so that we might as well remind ourselves of derivatives in general, right? Derivatives have a formal definition in calculus in terms of limits of functions. To be completely honest, you will use these in some of your problems, but don't think of physics as a math class with problems don't think of it like a math class with applications to physics. I mean, this is a physics class, and so this stuff is pretty expected. You know some of these standard rules here for calculating derivatives. This is an example right here of how to take the derivative of a simple, I have a simple 2t squared, s is a function of t, 2t squared, what's the derivative? It's simple power rule, right? So you get 4t. The only thing I would remind you of is that this 2 in the 2t squared has units. Numbers oftentimes have units in these functions because the left-hand side has units of position. That means if the time at second squared, that means the 2 has to have units of position per time squared. As we'll see, that's units of acceleration. And then down here, what units does the 4 have? Well, in the velocity v sub y, well, t has s seconds, And so the 4 has to have meters per second squared. They don't show that in here because they're just trying to remind ourselves of the review. But this is important graphical picture to see, is that the derivative of a parabola is a line. Right? That's just what we'll see a lot when we talk about different problems later in the chapter. So there's no need, if you know that it's parabolic, there's no need to try to find the slope at each one of these points in time. You just know that it's linear. And now looking at that parabola and, trying to figure out what that slope is, I'm not sure, but, you can certainly estimate it. So that concludes this section of Chapter 2 on instantaneous velocity. In the next chapter, we're going to turn it around and ask how we can find position from velocity. Because this section is more or less the first kind of direct problem. You start with position, work your way with the graph to find velocity. Next section, we're going to turn it around and ask ourselves, well, if we know velocity, how can we find position? And, you can kind of make a guess that if these are derivatives, then the other ones are going to be integrals. So as usual, thanks for your time. See you back here for the next video. Take care.